and to understand the leap from the chemical survivalism of the oxygen-rich pre-burner to the strategic dominance of the Raptor 3, one must look past the metallurgy and into the raw physics of energy transfer. In the previous sections, we established that full-flow staged combustion is a universal solvent of engineering problems, but it is also a massive force multiplier for thermodynamic work. If the pre-burners are the heart of the engine, the efficiency reimagined phase is where that heart translates its pulse into the staggering 280 tons of thrust that define the Raptor 3 performance. And in a conventional rocket engine, efficiency is often a zero-sum game. You trade weight for power or reliability for performance. The Raptor 3 breaks this cycle by leveraging the full-flow architecture to create a virtuous loop where the very volume of propellant moving through the system becomes its greatest asset. And the torque advantage, driving the 300-bar beast. The most immediate benefit of the full-flow cycle is the sheer amount of mass available to drive the turbopumps. In a gas generator cycle, like the SpaceX Merlin, or a partial staged cycle, like the Space Shuttle main engine, only a small fraction of the propellant is diverted to power the turbines. This creates a bottleneck. To get more pressure in the main combustion chamber, you have to spin the turbines faster, but you have very little working fluid, or gas, to do it with. You are essentially trying to turn a massive windmill with a leaf blower. And in the Raptor 3, this bottleneck is deleted, because all of the liquid oxygen and all of the liquid methane are vaporized into gas before they reach the main chamber. 100% of the propellant mass passes through the turbines. And for the mechanical engineer, this is a torque revolution. In a partial flow engine, the turbines must be incredibly efficient and run at extreme temperature differentials to extract enough energy from a small amount of gas to drive the pumps. In the Raptor 3, the turbines are flooded with mass. Even at lower temperature differentials, the sheer momentum of the full flow provides the pumps with an abundance of torque. And think of a high-performance turbocharger in a supercar. In a standard setup, the turbo uses a portion of the exhaust to force-feed the engine. Now imagine a system where 100% of the exhaust gas is captured and redirected with zero bypass. The result is a virtuous cycle of power. The more propellant you feed the engine, the more torque the turbines generate, which in turn allows the pumps to shove even more propellant into the chamber at even higher pressures. This is how the Raptor 3 achieves a chamber pressure of 300 to 350 bar-a-feet that would be physically impossible if the turbines were only sipping a fraction of the propellant flow. In the cooling bonus of high mass flow, counterintuitively, the full-flow nature of the Raptor 3 provides a thermal safety margin that its predecessors lacked. This is the cooling bonus of FFSC. In a partial flow engine, the gas driving the turbine is extremely hot and relatively low in volume. To get more power, you must increase the temperature, pushing the turbine blades closer to their melting points. And in the Raptor 3, because the mass flow rate is so high, the gas doesn't need to be as hot to do the same amount of work. The energy is carried by the mass of the gas rather than just its temperature. And for the computer science professional, this can be viewed as an O of one scaling property. In many systems, as you increase the load, the overhead, heat, or friction grows exponentially. In the Raptor 3, as you increase the mass flow to get more thrust, the system's ability to move heat away from critical components scales linearly with the power. The turbines are essentially bathed in a massive, high-velocity stream of gas that acts as a thermal ballast. And while 500 degrees Celsius gas sounds incredibly hot in the context of a rocket engine, it is significantly cooler than the gas found in the turbines of the RS-25. This lower operating temperature, made possible by the high mass flow, is what allows the Raptor 3 to be a truly reusable engine. It is not just about surviving one flight. It is about operating within a thermal window where the metal does not lose its structural integrity over dozens of cycles. In gas-to-gas combustion, the perfect mix. The ultimate goal of any rocket engine is to turn chemical potential energy into kinetic energy as efficiently as possible. This happens in the main combustion chamber, where the fuel and oxidizer meet. And in a traditional engine, you are trying to mix a liquid and a gas, or two liquids at supersonic speeds. Imagine trying to mix oil and vinegar by throwing two buckets of the liquids at each other in the middle of a hurricane. The mixing is never perfect. You get streaking, areas where there is too much fuel or too much oxygen, which leads to uneven heating, hot spots on the chamber walls, and unburnt propellant exiting the nozzle. This is wasted energy. In the Raptor 3, by virtue of its FFSC architecture, performs gas-to-gas combustion. By the time the methane and oxygen reach the main injector, they are both high-pressure gases. Gases mix orders of magnitude faster and more thoroughly than liquids. And when these two gaseous streams meet, the combustion is near instantaneous and incredibly uniform. This allows for a shorter combustion chamber, which saves weight and a much higher combustion efficiency. Every molecule of methane finds its corresponding molecules of oxygen. There is no waste. The Raptor 3 isn't just burning fuel. It is executing a precision chemical reaction with nearly 100% completion. This efficiency is what gives the engine its world-class specific impulse, the rocketry equivalent of fuel economy. and eliminating the parasitic loss of seals in almost every other liquid rocket engine design. There is a parasitic loss associated with the turbopumps. Because the fuel and oxidizer must be kept strictly separate to prevent a catastrophic explosion, engineers use complex seal systems and purge gases, often helium, to ensure that the two fluids never meet on the pump shaft. This purge gas is vented overboard, carrying energy away from the vehicle. And furthermore, in a gas generator cycle, the exhaust from the preburner is simply dumped out of a small pipe on the side of the engine. This dumped gas contributes almost nothing to the total thrust. It is a necessary waste of tax paid to keep the engine running. And in the Raptor 3, there is no tax, because it is a closed-loop system. Every gram of propellant that enters the engine eventually exits through the main nozzle at several kilometers per second. There are no overboard vents, no helium purges for the primary seals, and no wasted preburner exhaust. The full-flow moniker is literal. The entire mass of the propellant is used for thrust. This zero-waste philosophy is what allows Starship to carry such massive payloads. When you are moving 100+ tons to orbit, a 1% increase in engine efficiency translates into thousands of kilograms of extra cargo. And the virtuous cycle of pressure and density, the efficiency of the Raptor 3 also stems from its ability to handle supercritical fluids. At the pressures found inside the Raptor's plumbing, the distinction between liquid and gas begins to blur. The propellants enter a supercritical state, where they have the density of a liquid but the diffusivity of a gas. And by operating in this regime, SpaceX can shrink the size of the engine components. A high-density fluid requires smaller pipes, smaller pumps, and smaller turbines to move the same mass. This is why the Raptor 3 looks surprisingly compact for an engine that produces 500,000 pounds of thrust. And this compactness creates its own efficiency. Less mass in the engine itself means more mass can be dedicated to the payload. But more importantly, the high pressure in the combustion chamber allows for a higher expansion ratio in the nozzle. The higher the pressure you can maintain in the chamber, the more work you can extract from the gas as it expands against the nozzle walls and pushes the rocket forward. And the Raptor 3 high chamber pressure is the key that unlocks the door to high efficiency in both the vacuum of space and the thick atmosphere at sea level. It is a pressure-dominant architecture that treats the atmosphere not as an obstacle, but as a backdrop that it simply overpowers. And reliability through simplicity, the FFSC paradox. It is a common trope in engineering that complexity is the enemy of reliability. At first glance, the Raptor 3, with its dual preburners, complex manifolding, and exotic metallurgy, looks like the most complex engine ever built. However, from a systemic perspective, full-flow staged combustion introduces a profound simplification. And in a partial flow engine, the interstage seal is a single point of failure. If the seal between the fuel turbine and the oxygen pump fails, the engine explodes instantly. Because the Raptor 3 uses an oxygen-rich preburner to drive the oxygen pump and a fuel-rich preburner to drive the fuel pump, a minor leak across a seal is no longer an immediate death sentence. If a little bit of oxygen-rich gas leaks into the oxygen pump, it is just more oxygen. The chemical incompatibility that haunts other engines is largely mitigated by the symmetrical nature of the full-flow cycle. And this chemical symmetry means the engine is fundamentally more robust. SpaceX has traded component complexity, making the parts harder to build, for systemic reliability, making the engine harder to kill. For a vehicle intended to carry hundreds of humans to Mars, this is not just an engineering choice, it is a moral imperative. And the engine logic of Starship. The Raptor 3 is not an engine designed in a vacuum. It is the logic that makes the Starship architecture function. Without the efficiency gains of the full-flow cycle, Starship would likely be too heavy to reach orbit with a meaningful payload, or it would require a much larger, more expensive fleet of tankers for orbital refueling. And by maximizing every drop of energy, SpaceX has created an engine that behaves more like a jet turbine than a traditional rocket. It is a machine designed for high-cadence, gas-and-go operations. The efficiency is not just about saving fuel. It is about reducing the thermal and mechanical stress on the engine components by ensuring that no energy is bottlenecked or wasted as heat in the wrong places. And the efficiency reimagined section of the Raptor story is the bridge between the how of its construction and the why of its performance. We have seen how it tames the universal solvent of hot oxygen and how it uses the full mass of its propellants to generate unprecedented torque. But all of this efficiency creates a secondary, even more daunting challenge. And when you mix gases this perfectly, and when you compress them to 300 bar, you create a flame that is hotter than the melting point of any known metal. The very efficiency we have celebrated is also a recipe for a thermal catastrophe. The engine is now so good at releasing energy that it threatens to liquefy itself in seconds. And to solve this, SpaceX had to move beyond just surviving the chemistry and start manipulating the heat. This leads us to the most critical cooling challenge in aerospace history: how to keep a 3,000 degrees heart from melting its own ribs. This thermal tightrope act is the focus of our next deep dive. And the mastery of full-flow staged combustion has provided the Raptor 3 with the engine logic required for interplanetary travel. But this peak efficiency comes at a staggering thermal price. The same perfect gas-to-gas mixing that drives the engine's record-breaking thrust also generates an internal environment that defies the limits of conventional materials science. To prevent the engine from becoming a 200-ton puddle of molten superalloy, SpaceX had to reinvent the way heat moves through a machine, a challenge we will dissect in 5.1, the melting point problem, surviving 3,000 degrees.